Alright, silly people, here's the situation. Um, for this problem, we are going to start with the example code from example 3.2, I think, and just do a bunch of modifications to it. So this is that, but I did have to modify it a little bit already to make it work with VPython rather than visual. The main difference between it is that the position argument no longer accepts a list of I, J, and K. Instead, it has to be a vector object from VPython. So now instead of it being equal to list ijk, it's equal to vp.vector of ijk as a function, right? And so I'll show you that this runs the same way that the example code worked that Mark Newman provided, because it's just there looking like a bunch of spheres in a lattice. Pretty cool stuff. But that's fine. And I'll put this over here so I don't have to look at it anymore. Close this. So the first modification we need to make to it is we need to make it so that there are alternating sodium atoms and chlorine atoms in the cubic lattice, and we need to differentiate them in some way, like as we go. The way that I chose to do this is just to make them different colors. So in the last for loop, I'm going to make a couple of if statements. If I plus j plus k mod 2 is equal to 0, then we make the color of these spheres, let's just make them red. So vp.color.red, right? And then otherwise, we'll make them blue. This is very similar to the Madelung constant video that I did a little while ago, right? And just in the sphere function, you changed the color parameter to be our color variable dependent on, the parity. And then that should run, and we get this guy. So yeah, each of these blue spheres are surrounded by 6 red spheres, and each of the red ones is surrounded by 6 blue, providing they're not on one of the edges. And this is the sodium chloride lattice, guys. So the blue could represent the chlorine and the red sodium, or vice versa. It doesn't really matter. They are distinguishable, right? And so that's fine with me. The next part of the problem is to instead modify this so that it represents like a face-centered cube instead. So I'm going to take the code as it is and copy it down a little bit. Bam. And we're going to modify it again. So I'm going to take away the color statements because we don't really need those anymore. And I'm actually going to keep that if statement for something that I'll explain in a second. I'm going to get rid of the color argument in the sphere function. So for the face-centered sphere, it only wants you to display spheres that are on the corners of the cube, and also ones that are in the center of each face of the cube. So actually, what you want is every odd instance of I plus j plus k to result in a sphere popping up. So I'm just going to tab this forward into the if statement, right? And then it only wants a very small face-centered cube. So I'm going to set L to 1. That way it's only going to show 4 corners to each edge, or 4 corners to each face, and then a sphere in the center of each face. And then that should be good. Let's give it a run. And there it is. Yeah, so notice that there's no sphere in the center, so that's nice. And then there are spheres on all corners of the cube, and then spheres in the center of each face of the cube, just like we wanted. And that looks good. All right.